When you see a building stand tall for decades, the concrete is getting all the credit, but its true lifespan relies entirely on the hidden materials buried inside that concrete shell. By itself, concrete is excellent at handling compression. It can easily support heavy, static weight pushing straight down from gravity. Without steel inside, concrete is completely helpless against tension or bending forces. It will simply snap under the pressure. And buildings face those bending forces constantly. High winds push against the exterior walls, and the soil beneath the foundation is always shifting and settling over the years. That hidden steel skeleton is there to absorb all of those dynamic loads. It gives a highly brittle material the exact flexibility it needs to survive side-to-side stress. The exact choice of steel you put into a pour dictates the structural lifespan, the maximum flexibility, and the life safety of your project. Walk into any construction supplier yard, and you are immediately faced with 3 distinct categories of steel bars, all sitting at very different price points. Looking at this comparison matrix, the main competitors are mild steel, HYSD, and TMT. Builders have to decide if older, cheaper legacy standards are still viable, or if they need to pay the premium for expensive modern mandates. We are going to cut through the supplier marketing hype. By looking at the exact physical properties of each grade, we can match the specific steel to the physical scale of your next build. You want to avoid overspending your budget on small DIY projects, while making absolutely certain you aren't compromising safety on large-scale developments. We start our matrix with mild steel. This is the baseline option, characterized by a completely plain, smooth outer surface. It carries a relatively low yield strength, maxing out at roughly 250 megapascals. That lower strength means the steel is exceptionally soft and ductile. You can easily cut it and bend it by hand directly on the job site without specialized equipment. That smooth surface comes with a severe trade-off. It prevents the steel from forming a strong structural friction grip with the wet concrete curing around it. It also has a second major vulnerability. The raw material corrodes and rusts rapidly over time when exposed to moisture. You cannot use mild steel to support heavy dynamic loads safely. However, the sheer cheapness and workability make it an ideal fit for light, non-load-bearing residential walls or small driveway slabs. Moving to the middle column, high-yield-strength deformed bars, or HYSD, were engineered as the historical upgrade to mild steel. The surface is covered in deformed ribs. These ridges physically lock into the concrete as it dries, solving the bonding issues found in smooth mild steel. HYSD also provides a massive jump in yield strength, easily handling loads up to 500 megapascals. That means it can reliably support heavy structural beams and thick columns. To get that extra strength, manufacturers altered the chemical composition. That specific process introduced a new flaw into the bar: increased brittleness. A stiff, highly brittle material reacts terribly to sudden dynamic flexing forces, snapping into jagged pieces rather than safely bending. HYSD serves as a highly capable legacy standard for carrying static weight, but it struggles to safely absorb and dissipate the sudden, violent shifts of seismic activity. That limitation leads us to the current industry standard, thermomechanically treated bars, or TMT. Instead of relying purely on chemical tweaks for strength, TMT is created using a specialized rapid cooling manufacturing process. This diagram reveals the cross-section. Rapid cooling creates a tough outer layer of martensite, pushing yield strength past 600 megapascals. Because cooling stops at the surface, the interior remains a soft ferrite perlite core. This soft center lets the bar retain extremely high ductility and flexibility. This dual-nature structure also prevents surface rust from penetrating deep into the bar, offering superior long-term corrosion resistance. During an extreme dynamic event like an earthquake, this unique material allows massive structures to sway back and forth without collapsing. You will pay a higher initial financial cost for TMT, but it solves the historical engineering compromise, delivering maximum static load capacity alongside verified seismic resilience. Technical specs only matter when they are applied on a job site. Let's match your specific project to the correct steel. This flowchart maps out the decision. If you are a DIYer or contractor pouring light, non-load-bearing structures, you start at Node 1 and follow the path to mild steel. You save significant time and money on materials. The lower overall lifespan is an entirely acceptable trade-off for a low-stakes build. For the mid-tier builder handling standard reinforced concrete construction on a strict budget, living in a stable environment with low seismic risk, follow Node 2 to HYSD. You achieve the heavy load capacity required for residential beams, choosing to sacrifice modern seismic flexibility to meet your budget. Finally, if you are a high-stakes developer pouring heavy structural columns or building anywhere near an earthquake zone, Note 3 directs you to TMT. Paying the highest premium here secures top-tier life safety and guarantees the multi-generational structural integrity of the project. The best steel is entirely contextual. Success means carefully matching the physical material to the specific environmental and load requirements of your site. Dogmatic advice that demands you buy the most expensive material for every single project is flawed. Cheap, lower-tier options remain highly effective and financially smart when they are kept strictly within their proper context. Superior engineering is about applying your resources efficiently for the task at hand.